This meeting is being recorded.
Okay, so now that we have studied all the different types of categories of instructions, memory reference instruction, register reference instructions, and IO instructions. So now what we'll be doing is we'll be trying to solve some examples which are based on it. Once you understand the instructions, once you understand these types of questions, it would be very easy for you to solve it. Okay, so this is one of the textual question. Let us try to solve it first. uh, 5.9 from the textbook which we're using, Morris Mann. Okay, the content of AC in the basic computer is hexadecimal A937. So whenever this type of question is given to you, first from the question given, extract the metadata. Okay, so here what is given to us? We are given that the content of AC, why am I not able to write? Just a minute. Okay, I assume that the screen is visible now. So whenever this type of question is given to you, just extract the metadata from it first. So in this, what is given to us? The content of AC in the basic computer is this. So let us first write the content of AC. And the initial value of E is 1. So E is our extended flip-flop. These two things are given to us. Determine the contents of AC. You have to determine the contents of AC, E, PC, AR, and IR in hexadecimal after the execution of the CLA instruction. All of us know that CLA is a register reference instruction. Okay, so what we have to do is the initial values are given to you. After execution of this register reference instruction, identify the values of these registers and flip-flops. Repeat 11 more times starting from each one of the register reference instructions. We know that we have total 12 register reference instructions in our basic computer. Which are those? They are clear accumulator, clear E, complement accumulator, complement E. Then circular shift right, circular shift left, increment, 4 types of skips, and halt. Okay, so what we have to do is for each of these, we have to execute each of these register reference instruction in context to the initial values given to you, and then determine the value of each and every register which are mentioned over here, register and flip-flops that are mentioned over here. Okay, so now how are we going to write the answer to this question? Okay, one more thing is given to us. The initial value of PC is hexadecimal 0 to 1. Initial value of PC is what? Before you start executing the instruction CLA, CLE, CMA, CME, the initial value of PC is 0 to 1. Okay, so these are the data given to us, and then we will start finding the values of each of the registers given after execution of these instructions. Okay, so I'll show you how to write the answer to these type of question. We were asked to find the value of E, AC, PC, AR, and IR. Okay, I have written E before AC because we generally place the E flip-flop ahead of AC. Why? Because it is an extended flip-flop. It stores your uh, addition overflow value, division overflow value. So I kept it over here, right? In the earlier, when I had noted down the registers, I had placed E over here. But for our convenience, I placed it over here. Okay, so we will be writing the answer in a tabular form. Now, in the first row, we will be writing initial values given to us. So what is the value given to us? Initial E is 1. Value of AC is A937. Value of PC is 0 to 1. AR and IR values are not given to us. Okay. So this is how we will be starting this type of question. My answer representation would be in a tabular form. Okay, now let us start with the first instruction, CLA. What does CLA stand for? CLA stands for clear accumulator. Now, when this instruction is executed, what happens is the content of accumulator becomes 0, clear A. Okay, so this would become 0. During the fetch phase of CLA instruction, what we are doing is we are incrementing the value of PC. As soon as this instruction is fetched in IR, the content of PC would be incremented by 1 and it would be ready for the next instruction to be executed, right? So the value of PC would become 0 to 2. When this instruction is fetched CLA, what is the instruction code for CLA instruction? It is a register reference instruction, and the code, IR code for it is 7800. As soon as the instruction is fetched from memory, it is stored in IR during the fetch phase. Okay, we all know what happens in the fetch phase. PC to AR, right? What we do is PC to AR and then M of AR to IR. So when we are executing CLA instruction, we know that for the instruction CLA to be executed, the instruction code should be 7800. So that 7800 instruction code is fetched from memory and stored in IR. So here what we will be having in IR 7800. So this is during the fetch phase. What happens in decode phase? The last 0 to 11th bit would be stored in AR. So what we will have in AR here? 800, right? So this is how we'll be writing the value. The value of E doesn't change. Okay, it remains as it is. We did not carry out any operation on E yet. So whatever was the initial value of E would remain as it is. Now let us move on to the next instruction, CLE. CLE stands for clear E. Clear E is what if the value of E is 1, we make it 0. The value of AC would remain unchanged. It would remain the same, A937. We are not making any changes on accumulator. Okay. Then the value of PC, again, it was 0 to 1. It will become 0 to 2. See, we have to execute all the instructions in context to initial values given to us. Okay, these instructions are not in sequence. CLA के बाद ही CLE होगा ऐसा नहीं है, right? So we are writing the CLA instructions. We are executing the CLA instruction on the basis of the initial data given to us. Okay, so what is the instruction code for CLE? It would become 7400. And the value of AR? Okay, then comes CMA, complement accumulator. Okay, when complement accumulator is given to us, I'll show you how we will be doing it. Complement accumulator. So whatever is the value of accumulator, we'll first write it in binary. So A is 10, 1010. This is 9, 1001. This is 3 and 7, 0111. Now we will be complementing these things. So 0101, 0110, 1100 and 1000. So now what is the value of the complemented accumulator? Let us write it here. 0101 is 5. 0110 is 6. 1100 is 12 is C, and 1000 is 8. So my updated value of accumulator would become 56C8. The value of E would remain unchanged. We are not changing the value of E. PC would become 022. AR, this is 7200. Code for CMA is 7200. So the value of AR is 200. Any doubt in this? I assume you are understanding the process. So for finding the value of complemented accumulator, I first wrote the value of A937 in its equivalent binary, complemented it, and whatever I got as my answer is the answer of CMA instruction. The value of accumulator would be that. Okay. Moving ahead, the next instruction is CME. Complement E. Initial value of E is 1. Let us complement it. It would become 0. The value of AC would remain unchanged. A937. PC 021 would become 022. The code for CMA is 7100 and the value of IR is 100. Okay, I assume that you will be able to write the instructions along with me on your own now. Chalo. CLA, CLE, CMA, CME. The next instruction is CIR. CIR is circular shift right. For circular shift right, again, I will have to write the value of my accumulator. We all know that for circular shift right takes place on E and AC. So first what I'll do is I'll write the value, initial value of E and A937 in binary. A is 1010, 9, 3 and 7. Now I want to perform circular shift right. So this takes place like this and it will come over here. Okay. So what would be the updated value? This one over here, 1101, 0100, 1001 and 1011. So this is what? 1101 A, B, C, D. Okay, 12, 13. Then 4, 9 and this is 8, 9, 10, 11, B. Okay, so this is D49B would be the updated value of my accumulator. And what is the value of E after we perform the shift? 1. So this is 1 and this is D49B. So one main important thing that you need to keep in mind is whenever we are performing circular shift right or left, we have to perform it together on E and AC. Okay. So let me remove it. Okay. The value of PC022, the code for it is 7080. So in AR we will have 080. Now let us quickly do CIL. CIL again the same process. Write A937 and E together in binary. So initial value of E is 1. A937 is 1010, 1001, 0011 and 0111. Now perform shift left. Shift left is what? In this direction and this one will go over here. Okay. So what we are doing is, yes, this way. So once then this would become 0101. This would become 0011. No, sorry, 0010, 0110, 1111. Okay, so the answer to this is, where did we get this least significant bit from? That was from E. Okay, so here now my value for after circular shift left would be E is 1. This is 0101. 0101 is 5. 0010 is 2. 0110 is 6 and 1111 is F. PC This is 040 and 7040. Okay, now which is the next instruction? After CIR, CIL, we have increment. Increment is you just have to increment the value of your SE. This would remain same. A937 would now become A938. PC would remain as it is. The code for INC is 7020, so that would be in IR, and AR will have 020. Okay, now quickly the four types of skip. Skip if accumulator positive, skip if accumulator negative, skip if accumulator 0. Sorry, I made a mistake in writing this. Skip if accumulator positive, skip if accumulator negative, skip if accumulator 0, and skip if E0. And last instruction is halt. Okay, so we'll be writing the values of registers and flip-flops after execution of each of these instructions. Quickly, SPA is 7010, SNA is 7008, SZA is 7004, this is 7002, and this is 7001. So let us quickly write this. This is very simple to write. The last 11 bits, 0 to 11 least significant bits, that is 12 least significant bits, would come in AR. Now let us quickly see this. Skip if accumulator positive. When I see this A938, what is A938 in binary? It is 1010 and something something something. To check whether the value is positive or negative, we check the most significant bit. If the most significant bit is 1, it indicates my accumulator is negative. If the most significant bit is 0, it indicates that the accumulator is positive. Okay, so in this case, the accumulator's value is negative. Hence, will we skip the next instruction? No. My values of all these would remain as it is. We are not performing any action. Why? Because the content of accumulator is negative. A937. Okay, PC 022. Now check, skip if accumulator is negative. We know that my accumulator is A937. The value of A starts with 1, hence the content of accumulator is negative. What we have to do if the content of accumulator is negative? Skip. What does skip means? Increment the value of program counter. Okay, so the next instruction which was going to be executed 022 would be skipped and the value of program counter would become 023. Content of accumulator would remain as it is. Okay, now next one, skip if accumulator 0. Is the value of accumulator 0? No, it is A937. So nothing would happen. My values would remain as it is. Program counter 022. Skip if E is 0. Is the value of E 0? No. So nothing would happen. It would remain as it is. Program counter 0 to 2. This would become 002 and 700. Last one, halt. What is halt? Halt instruction sets the value of start stop flip flop to be 0, right? And hence here we are not showing the value of S. So all these things would remain as it is. The only change would be reflected in the start stop flip flop, which we are not showing over here. So this is how we will be solving this question. We noted down all the register reference instructions. We started off with CLA and repeated it 11 more times, so total 12 instructions we performed. Was it simple to execute? So for any type of question given over here, once you understand it, how to write the answer, it's very simple. You know all the register reference instructions and you know what steps, what instructions are performed for which are the different steps at different timing signals that takes place for each and every instruction. So this is how we'll be solving this question. Okay, so in the next video, I'll be showing you how to solve the same type of question, but now we'll be doing it for memory reference instruction. Okay.